Last week we started our new unit on circular motion, and we did a whole bunch of stuff within that, including define frequency, define period, speed in the context of uniform circular motion. But the thing that we ended off with last week was centripetal force. Centripetal force was the force that acts on an object that's moving in a circle, and it acts toward the center of the circle always. So if you got an object moving in a circle like this, okay, at this point, let's say it's going counterclockwise. Okay, at this point where you see that dot, its velocity would be a straight line right there. Looks something like this. At this point, its velocity would be down like this. At this point, its velocity would be like this. Its velocity is always, as we said last week, a tangent to the circle. But the force will always be toward the center of the circle. It doesn't matter where the object is in the circle, the force is toward the center of the circle. That's why we call it centripetal force. Centripetal means center seeking. Now, we learned an equation for centripetal force last week as well. Fc is equal to m times, well, F is equal to ma, right? But A is v squared over r. F is equal to mv squared over r. Remember what we said, though, as well about this centripetal force. It's never a fundamental force. It's always caused by something else. In the case of the Earth going around the sun, what's it caused by? Gravity. Good. In the case of my keys going around my hand, I always use that as an example, right? Swing the keys around my hand on the end of the string. What's the centripetal force caused by? My hand. Good. In the case of the electron, if you know anything about atomic physics from chemistry class or from Science 10, the electron orbits around the nucleus, right? The centripetal force is caused by an electric force. In the case of a car going around a turn, the centripetal force is caused by friction. Good. There's always something that causes that centripetal force. Now, sometimes we don't know what it is. Sometimes we don't care what it is. But if we do know what it is, and we do care what it is, then we can set that centripetal force, mv squared over r, equal to whatever that other force is. So maybe in the case of the car going around the turn, we can set the centripetal force equal to the force of friction. In the case of the Earth going around the sun, we could set the centripetal force equal to the force of gravity, right? If gravity causes centripetal force, then there's no reason why we can't set the two equal to each other. All right, that brings us to 3 questions that we had on page 259, which all involve friction. They all involve an object going around a turn. So they all involve, in other words, either Fc is equal to mv squared over r, or they involve Ff is equal to mu times the normal force, or they involve Fc is equal to Ff. Really, we got 3 choices, right? Whichever happens to work the best. Do we have any issues with any of those 3 questions that we worked on? Questions 1 to 3 on page 259. Yep. Yes, I can. Okay, so the answers are at the bottom there now in case you weren't sure if you had any issues with them. Just have a quick peek. And then let me know if there's any of these that we need to go over. If you say no, we'll still go over one of them, okay, just as practice, just as a little bit of a review. But if you say that there's a couple of them that we need to go over, or one in particular, then that means that you get to pick as opposed to me getting to pick which one we go over. All right, then, 1, 2, and 3 it is. All right, number 1 says an Edmonton Oiler carves a turn with a radius of 7.17 meters while skating and feels his skates begin to slip on the ice. So in other words, what's happening there? He's barely exceeding the maximum force of friction, right? He's barely exceeding the maximum centripetal force. So in other words, he's starting to go off in a straight line as opposed to going in the circle, right? We want to know what his speed is if the coefficient of friction between the skates and the ice is 0.80. In other words, we want to know what the coefficient of friction is required to keep him from going off out of that circle. So what are we going to do? Well, We got three options here, right? We got the FC is equal to mv squared over r. We got the F is equal to mu times the normal force. And we got the FC is equal to FF. Now, you don't have to, by the way, set those equal to each other right now. You could calculate one force, okay, and then say the force of friction, and then set it equal to the centripetal force. But I think it's just as easy to do it right off the top here. So let's do that. mv squared over r becomes equal to mu times the normal force. And on a horizontal surface, and ice is, a hockey rink is clearly a horizontal surface, the normal force would be equal to m times g. Now, the mass of the Edmonton Oilers hockey player is 100 kilograms, but the mass, if you set it up like this, actually cancels. If you calculate the forces separately from one another, the mass doesn't cancel. But together, the mass does. So it becomes v squared over r equals mu times g. We're looking for v. So we take the r up by multiplying. Mu times g times r. Square root that. Mu is 0.80. G is 9.81. And r is 7.17 meters. We square root that. And when we do that math, we end up getting a value of 7.5 meters per second. So what we're saying here is this. Anything below 7.5 meters per second, the force of friction is strong enough to keep the guy going in a circle. Anything above 7.5 meters per second, the force of friction will still act, but it's not big enough to keep him going in a circle. He may not go off in a straight line because friction's still acting, but he's not going to go in the circle because he's going too fast, right? Force of friction isn't big enough to supply that centripetal force necessary. How can we set them equal to each other? Hey, the question was, how come we can set these two forces equal to each other? Remember fundamentally what we're dealing with here, okay? We're talking about centripetal force, centripetal acceleration, circular motion, right? But fundamentally what we're dealing with in this question is friction, okay, not centripetal force. The force of friction is what causes this skater to not go in a straight line. Now, that force of friction specifically causes the skater to go in a circle, not just not in a straight line, but specifically to go in a circle. So if the force of friction causes the person to go in a circle, and anytime it's going in a circle, we call it a centripetal force, then basically all we're doing there, Stephanie, is taking the force of friction that we've dealt with 1,000 times back in our last unit and renaming it centripetal force. Now, if they're the same thing, we're just calling them different things, right? Force of friction, call it force of friction. Now we're calling it centripetal force because it happens to be directing it in a circle. If we're just renaming it, then there's no reason why the equations aren't going to be equal to each other. Does that make sense? If we're talking about, just as we talked about in our review, the Earth going around the sun, then we could set, we wouldn't have to, but we could set Fc equal to Fg, the force of gravity, okay? Which force of gravity that we'd use in there, we haven't learned that equation yet, but the idea would be the same. Okay. Okay, I want to do number 2 here, and then I want to leave you with number 3 and give you about 2 minutes to finish it up if you weren't able to get it here. Then we'll take a look at that one after we're done that. Number 2 says, automotive manufacturers test the handling ability of new car design by driving a prototype on a test track in a large circle with a radius of 100 meters at ever increasing speeds until it begins to skid. Here's the car, 1,200 kilograms, found to skid at a speed of 95 kilometers per hour. What's the coefficient of friction between the car and the tires? We can, if we want, say F is equal to mu times the normal force. We can say F is equal to mv squared over r. Those are both valid. But I have a gut feeling here that we're going to say Fc is equal to Ff. Okay, if you don't want to do that, don't do it. Calculate Fc, get a number for Fc, and then set it equal to Ff and solve for the coefficient of friction. I just find it a little bit easier to do it all at once here. So we're going to say mv squared over r equals mu times the normal force, which on a horizontal surface is m times g. Masses cancel. Honestly, the reason I like to set them equal to each other is because the masses cancel that way. If you didn't set them equal to each other right away, then you'd have to put in the mass into the equation. Okay, we're solving for mu, solving for this. So we're going to take the g over by dividing. V squared over g times r. Oh, wait, 95 kilometers per hour. I don't like that. It's equal to 95,000 meters over 3,600 seconds. That's going to equal what, about 21 and point something? 26.38 meters per second. Always want to be in meters per second here, right? Always. If in doubt, right, at the beginning of the year, we said that occasionally you can be in kilometers per hour. If in doubt, always go meters per second, because it always works for you. Whenever you're plugging into an equation like this, you definitely have to be. If you get 26.38, you've got to square that, divide it by 9.81, and multiply that by the radius of the turn, which is 100 meters. And we get the coefficient of friction to be 0.710. Does that seem like a reasonable number? Usually it's between 0 and 1. Pavement, 0.7, 0.8. See, seems good, seems good. Okay, let's take 2 minutes right now. If you weren't able to get number 3, see if you can get that right now, okay? And then we'll take a look at that once you've had that chance. Taking a look at question number 3 now. It says a 600-gram toy radio-controlled car can make a turn at a speed of 3 meters per second on the kitchen floor with a coefficient of friction is 0.90. What's the radius of the turn? Same question as we've had in question 1 and 2, right? Except that this time we're finding r instead of v or mu. Okay, it doesn't matter. It's just a matter of rearranging, right? Once again, we can say Fc is equal to mv squared over r. We can say Ff is equal to mu times the normal force, or we can set them equal to each other. Okay, if you find that you do this, Fc equals Ff, and it doesn't work for you because you get 2 or 3 unknowns, then just try one of the equations. Okay. It doesn't, we've said this 1,000 times before. If you try something that's valid and it doesn't work, then try something else. Okay. I think this is what's going to get me the answer. If it doesn't get me the answer, then just pick one of the 2 equations instead of putting them both together and try solving it that way. All right, we got mv squared over r equals mu times the normal force, which again on a flat horizontal surface, it's going to be mu times m times g. M cancels, so we don't need to know that it's a 600-gram toy. We don't need to convert it to kilograms because mass is gone. Looking for r. We get the r up to the top by multiplying. But then we've got to get the mu and the g down by dividing. So it becomes r is equal to v squared over mu times g. V is 3 meters per second. Mu is 0.90, and g is 9.81. When we do that math, we should get 1.0 meters. Regardless of how heavy this toy is, the radius should be exactly the same, 1.0 meters. Yep. That's right. Okay. Lewis's question, guys, if you didn't hear that, is, does it not matter how we do it as long as you get the right answer? As long as you do it in a legitimate way and not just get a lucky answer or not just punch numbers into your calculator, come up with an answer, and write down the number, I'm fine with you doing it differently. Like, what's the alternative to this? Oh, Lewis, maybe somebody says FF is equal to mu times the normal force. And the normal force is m times g. So they get a value of the force of friction, whatever it is. Okay, I don't know what it is because I didn't do it that way. But then they say, oh, wait, that force of friction has got to be equal to the centripetal force. Fc is equal to mv squared over r, and then they rearrange that equation to solve for r, but they plug that number into there. Okay, 2 separate steps, right? Go ahead and do it that way. That's fine. Okay, it's just as good as my way. Okay, the only benefit to my way really is that m's cancel and you don't have to plug in the mass into the equation. Okay, but as long as you do it in a legitimate way, of course you're going to get the full marks for that. Okay. Okay, I want to real briefly talk about this other force that you may have heard of before, but kind of wishy-washy on what it actually is. Not sure what it really is. Not centripetal force, but centrifugal force. Some people call it centrifugal force. Centrifugal or centrifugal. If centripetal force was the center-seeking force, right? Centripetal means center-seeking. Then centrifugal means center-fleeing. So in other words, the centrifugal force isn't the force that acts toward the center of the circle. The centrifugal force is the force that pushes an object moving in a circle, or that pushes an object in uniform circular motion out or away from the center. Now, there's a reason why I've put centrifugal and force in quotation marks. The reason is because the centrifugal force that pushes an object out from the center of the circle, which you guys have all experienced, right? You're driving in a car and you're going around a turn really quick, you get pushed toward the outside of the circle. Okay, you're on a roller coaster, as you will be tomorrow on your field trip. Go around a turn, a sharp turn, you get pushed toward the outside of the circle. You've all experienced this, right? You've all experienced this force that doesn't exist. It doesn't exist. There's no such thing as a centrifugal force. The centripetal force pushes us toward the center. The centrifugal force that pushes us outward, the one that we've all felt, doesn't exist. So how do we explain that? How do we explain a force that we've all felt and we've all experienced that doesn't exist? You're staying at one spot and it's kind of moving around you? Oh, good, good. Louis, what do you say there? Okay, so you want to go off on a tangent. So how does that push you to the outside, though? Yeah? Okay, good, good. Excellent. So here's the circle. Okay, here's the center of the circle. When I was a kid in elementary school, they don't have these anymore because kids got hurt, and you got to take away, all fun things where kids get hurt every once in a while. A few broken arms, it was worth it, right? It was worth it because I had lots of fun with them. We don't have merry-go-rounds anymore, although those merry-go-rounds with the big webs, the big cone-shaped webs, seem to be coming back a little bit. Can't get those things spinning as fast as the merry-go-rounds when I was a kid, though. They're a lot heavier. We used to have a merry-go-round on my elementary playground. This is the merry-go-round looking at it from above. It was 4 bars. And we would get that thing spinning so fast, or at least when we were 8 years old, it seemed like it was spinning so fast. Okay, it might not seem like so fast now, but that's what it seemed like. We get the thing spinning so fast that as we were holding on to it, say right here, there'd be like 20 people on this thing, on this small thing, trying to grab onto anywhere they could grab onto and not fling off. See, that's what happened, is kids would fling off and break an arm or something. I don't know how many times that kids actually, probably just about every day, somebody went in crying into school because they hurt themselves. Didn't happen very often that somebody broke an arm, but it did happen, but just not very often. You're going really, really fast around here. What happens? Well, you get flung to the outside, right? No, you don't get flung to the outside. Okay? There is no such thing as a centripetal force pushing you to the outside. So how do you go to the outside? Just as these guys said, you want to go in a straight line. As it's rotating, you end up going in a straight line. So by the time the end of the merry-go-round catches up with you, here's the bar. By the time that bar catches up with you, you're there. You're at the outside. But you went to the outside not because you were pushed to the outside, because of inertia. You want to go in a straight line. So your inertia takes you in a straight line. But the edge of the merry-go-round catches up to you. Your perception is that you were pushed to the outside. But the reality is you just wanted to go in a straight line and the edge of the merry-go-round caught up to you. Why does it feel like you're being pushed to the outside? Okay, forget about where you end up. Okay, when you're going in a circle like that, you feel yourself being pushed to the outside. Okay, imagine you're sitting at a stop sign and a car's coming up behind you and hits you from behind. Okay, that's what I'm doing right now. Okay, I'm sitting at a stop sign, minding my own business, waiting for the light to turn green. Somebody else, probably in a flat brim hat, isn't paying attention. Okay, they drive up and they hit me from behind. Okay, what happens? Well, my head remains at rest. Yes, you're right. My head remains at rest, my body goes forwards, right? I get pushed forward by that car. But what does it feel like to me? I feel like I'm being pushed back into my seat, right? I just flew to Toronto a week and a half ago to go to a Raptors game, the weekend that we had the Friday off. And you're taxiing out on the plane, and then you go to the runway. You're taxiing slowly, right? You get to the runway, you turn that corner, and then the pilot just gives her, right? You're going all of a sudden, 30 kilometers an hour, and then all of a sudden you're going 200 kilometers per hour in a matter of seconds. And get 0 to 200 in seconds. Okay? You feel like you're being pushed back into your seat, right? But you're not. Your seat is pushing you forward. Anytime there's an acceleration, listen carefully to this. Anytime you have an acceleration, you feel what we call a pseudo force in the opposite direction. A pseudo force is a fake force. Let me just write this down. Anytime there is an acceleration, there is a pseudo force in the opposite direction. In other words, as I was sitting at the stop sign and I was pushed forward, it appeared to me as if I was pushed backward into the seat. When I was rounding that corner to accelerate from 30 kilometers per hour to 200 or 300 kilometers per hour on the runway, it felt like I was being pushed back in my seat. Why? Because I was being pushed forward. I felt that pseudo force, that fake force, that force that doesn't really exist, me being pushed back into my seat, when it was really my seat pushing me forward, right? That's what we got here. You're being pushed toward the center of a circle. What does it feel like? It feels like you're being pushed out toward the outside. You're sitting at a stop sign, car hits you from behind, it feels like you're being pushed back into your seat, really you're being pushed forward. Okay? You're rounding a circle, it feels like you're being pushed to the outside, really you're being pushed to the inside. Anytime you have an acceleration, we have a pseudo force in the opposite direction, which in this case would be toward the outside of the circle, because there's really an acceleration toward the inside of the circle. Anytime you hear that word centrifugal, now you can say to the person sitting next to you, oh, that's so fake. Centrifugal force doesn't really exist. We just think it exists because of inertia. It takes us in a straight line. And anytime you have an acceleration, of course, everybody knows this. Every time you have an acceleration, there's a pseudo force in the opposite direction. Okay, say that. Okay, say that to the person you're sitting next to whenever you hear that word centrifugal force. Does it kind of make sense? Okay, here's the last thing we're going to do before our big trip tomorrow. This is going to be on that trip, so it's good timing to be doing this here now. We've analyzed at this point objects moving in a circle, but those circles have always been horizontal. Car going around a turn experiences a centripetal force which is caused by friction. Keys going around my head experiences a centripetal force caused by my hand pulling it in. But what if you got an object going in a circle that's a vertical circle? Maybe you got a roller coaster guess the wheels should be on the track, right, if it's a roller coaster. Okay. This would not be good. Okay, let's put the wheels on the track. It's a roller coaster going around in a circle, but upside down. Or maybe the roller coaster is going in a circle like this, and maybe the roller coaster cart is at the bottom of the circle, it's right side up, but it's still going around this vertical loop instead of horizontal. This throws a wrench into our analysis. There is still a centripetal force that pulls it toward the center of the circle. Always. There's still always that centripetal force that pushes it toward the center of the circle. But remember what we said, the centripetal force is always caused by something else. Well, in this case, that centripetal force is caused by two things, not just one thing. Not just friction as the car goes around a turn, or not just my hand as the keys swing around my head. Anybody want to take a stab at what the centripetal force is caused by here? What's one thing that helps? Just think about fundamentally what this is, right? What helps the car stay in a circle? What's one thing, Gary? The normal force, right? So the normal force acts toward the center of the circle, right? It helps provide the centripetal force. What other force acts, especially at the top of the circle there, to pull it down toward the center of the circle? Lewis? Gravity. Look, gravity pulls down. So the normal force and gravity combined give me the centripetal force here. On the bottom one, it's a little bit harder to understand because gravity still acts down, which is not toward the center of the circle, right? But the net force toward the center of the circle will be gravity and the normal force combined, and that net force will be the centripetal force. So we're going to say in both cases, at the top of the circle and the bottom of the circle, the centripetal force is caused by gravity and the normal force. Now, you could draw it at the side of the circle as well. We won't have any problems like this. Okay, there's the car. The normal force would act this way. The force of gravity would act this way. It would become a little bit more complicated analysis, right? Because we've got two different planes. But you can imagine how we'd go about doing that, right? It'd just be a two-dimensional problem then. All right. Let's go back to our last unit for a second. Our dynamics unit. Every time you saw a free body diagram, that's what this is, right? That's a free body diagram, two of them. Every time you saw a free body diagram with two or more forces acting, what'd you do next? What did you do next? What was the next step always? Whether it was an elevator problem, or it was a hill problem, or it was a pulley problem, what was the next step? Good. Good. Stephanie nailed it here. F net is equal to the sum of the forces. So let's do that here too. Let's say F net is equal to Fg plus Fn. Force of gravity plus the normal force. Let's do that for this one too, because the free body diagram, although the normal force is in the opposite direction, still has the same two forces. Fg plus Fn. We're not worrying about positive or negative yet, because we haven't plugged numbers in yet. Good. Stephanie's off the hook for the rest of the day now, because she just gave me a really good answer. What's the next step after we write F net is equal to the sum of the forces? What did we always write down next? MA is equal to the sum of the forces, right? We replaced F net with M times A. But hold on before you write this down. In this case, when we're going in a circle, MA is equal to, right, the force is equal to mv squared over r. So it's still MA, but it's a very specific A, centripetal A. Okay, same deal down here at the bottom. mv squared over r equals Fg plus Fn. This is no different than an elevator problem that you did in the last unit, or a pulley problem that you did in the last unit, except that we're tacking in a v squared over r in for A. All right, now it comes time to plug numbers into this. Now we got to worry about positives and negatives, because that's when we worry about it, right? When we plug numbers in. Make a little chart here. FG. When this object is at the top of the circle, FG will be what? Positive or negative? This is the easy one. When you're at the top of the circle, FG is pointing which way? Seth, which way is the force of gravity pointing at the top of the circle? Down. So it's going to be positive or negative? Good. So we're going to make it negative. In fact, FG is pointing downward at the bottom of the circle as well. So FG in these problems will always be negative for us. We got to label this positive here, but as soon as we plug the number in for it, we make it negative. Yep, what is the question? You could, but I would suggest you don't, because the question was, by the way, if you didn't hear that, was if you're doing a problem at the top of the circle, could you just make down positive because everything's down, right? And the answer is yes, you could. But my suggestion to Lewis was that you don't do that, because then you sometimes lose track of the sign conventions that we get used to using. Okay. My take on it is, let's stick with the same conventions, and that way we stay in the habit of making down negative. That way, when it really does matter, we're not as likely to forget that and get it mixed up. Okay. But if you did that, it would still be right, and I'd mark it right. But according to our conventions, FG would be negative at the top. Okay, what about Fn? When you're at the top of the circle, which way does the normal force point, Derek? Down. So we're going to make it negative or positive. Good. When you're at the bottom of the circle, which way does Fn point? Which way does Fn point now? It points up, so we're going to make that positive, right? This is the tricky one, Fc. Does Fc point up or down when you're at the top of the circle? Stephanie? Down. Points toward the center, right? If you're at the top and this is the center, then the center is down from you. So Fc is going to be a negative value. Just as Lewis said, they're all the same, so if we wanted, we could make them positive. I just don't suggest that. Yep. The centripetal force? Good question. Do we just make the centripetal force negative right here because we have a negative and a positive? No, that's a good guess, though. Which way is the centripetal force when you're at the bottom? Let's think about this. Here's the center of the circle. You're at the bottom. Which way does the centripetal force act? Toward the center, right? Is that going to be up or down? Jacob, up or down? Up. So we're going to make Fc positive there. Not because this is positive or because this is negative, but because the center is up from where we are if we're at the bottom of the circle. Okay. Guys, once you got the sign conventions down and what we have written down on the board over here with the equations, it's just a matter of plugging numbers in. And then you get the exact same problem as an elevator problem. If you could solve those elevator problems, you could solve these problems just as easily. The signs are a tiny bit trickier. But again, if you get that chart figured out, then you should be good. All right, let's try this question here. You got a picture here. It looks a little bit tricky, actually. You got 3 points, A, B, and C. But the good news is we're looking for the tension in the rope at position C. The tension in the rope, what are we really looking for there? If we go back to our free body diagram, what are we really looking for if we're solving for tension in the rope? What variable is it? Fg, Fn, Fc, what is it? No. No, not Fnet. Thought you had it there. No. What's left? What's left? Fn. Think about it, right? And this, we got a roller coaster on a track. The track provides the normal force. If we're swinging something with a string, what provides the normal force? What helps gravity out? It's the string, right? The tension in the string. So I don't care whether you're dealing with a track or a string that's helping gravity. Let's call it the normal force. If you'd rather call it Ft, that's okay. Okay, just understand that this equation would become F net is equal to Fg plus Ft instead of Fn. All right, I'm going to redraw this because I don't like that picture that they have there. I got this bucket of water. It's got a mass of 1.5 kilograms. We want to find the normal force that acts toward the center of the circle. When you're at the bottom, we have a force of gravity acting toward the center of the circle as well. We got a 1.5 kilogram mass. We got a radius of 0.75 meters, and we've got a speed of 3.00 meters per second. Solve for Fn. Yep. Yes, it is. Yes, it is. Good point. In what world is gravity ever pointing upwards? In the bizarro world, but this is not the bizarro world. Thank you, Lewis. Fg should be pointing downward. I haven't made that mistake. I've made lots of mistakes, but I haven't made that mistake since my first year university, when I, for whatever reason, labeled gravity acting up. And I remember on my exam, my professor said, "In what world do you live in?" That was his comment. "In what world do you live in that gravity acts upward?" Thank you, Lewis. Gravity does act downward, you're right. See how easy it is to make a silly mistake, though? All right, so we're going to say F net is equal to the sum of the forces. That's Fn plus Fg. Mv squared over r equals Fn. That's what we're looking for here, right? Fn. Plus m times g. Gravity is mg, right? Cancel out the mass there? Oh, good question. Can I cancel out the mass there? Can I cancel out the mass? Yep, can I? Why not? Good. It's got to be in every term. Can't cancel out the mass there. It matters. I mean, think about that. You got a guy on a roller coaster. He weighs 150 pounds, okay, going around that vertical loop. What provides more stress on the track? The 150-pound guy or the 300-pound guy? The 300-pound guy, right? The mass matters here. Yep. No, that's a good question too. If we say Fn is equal to mass times acceleration, no, the net force is m times a. The normal force isn't. Now, for us, most of the time, the normal force is m times g. But that was when we were standing on a flat horizontal surface, right? That just happens to be where most of the problems we do are. Right? Here, the normal force changes because of how fast you're moving, the radius of the loop. It changes, just like it does on an elevator, right? The normal force changes. Okay, so we got the mass here. It's 1.5. V is 3. R is 0.75. Mass is 1.5 again, times 9.81. But remember, we said that gravity is downward here. So we're going to make it negative. We haven't plugged a number in for Fn, so we won't worry about that one. Centripetal force, we're going to leave it as positive because it acts up when you're at the bottom of the circle. Let's get this number now. Solve it. Left side, 1.5 times 3 squared divided by 0.75 is going to be 18. Subtract 1.5 times 9.81, 14.93, I think. No, that doesn't seem right. 14.7715. Thank you. Take that over to the other side by adding. We end up getting Fn is equal to 32.715. We're going to round that to 2 digits, 33 newtons. right? Hard? No. If the elevator problems were hard, then this is hard too. If the hill problems were hard, these are easier than the hill problems. If the pulley problems were hard, then these are hard. But if those questions made sense to you, then these should too. These are the same thing, except we've got mv squared over r instead of m times a. Good news and bad news. Well, bad news is the same as it always is, right? We got questions to work on here. The good news is there's 3 questions. Question number 2 we're scratching out. And the reason is because they were looking for question number 2 when the object was at the side of the circle. And we don't need to deal with the questions where it's at the side of the circle. We're looking at the extremes, top or bottom. So take a look at 1 and 3, see what you can do with it. And then I'd love to do one more example problem with you before we wrap it up, but we'll see how it goes. Let's take a look at number 3, everyone here. It says a 0.9 kilogram rock is attached to a 0.40 meter rope and spun in a vertical circle. So the tension on the rope when the rock is at the top of the swing is 79 newtons down. What's the speed of the rock at the top? So here's the rock. Okay, it's 0.98 kilograms. The rope is 0.40 meters long, so that means that's going to be the radius, 0.40 meters, the radius of the circle. The tension on the rope, in other words, the normal force, we know is 79 newtons down. Okay, there's also a force of gravity. We want to know the speed of the rock. So let's say Fn, Fnet I should say, is equal to Fn plus Fg. The net force, not the normal force, the net force, which is mv squared over r, equals Fn plus Fg. Okay, we know what m is, right? It's 0.98 kilograms. V, we're trying to solve for V. R is 0.40 meters. Now, we've plugged numbers in for this expression. As soon as you put a number in for an expression, then I want you to worry about whether it's positive or negative. The centripetal force when you're at the top of the circle is downward. So let's make that negative. Okay, don't put the negative in until you plug numbers in. But we've plugged numbers in here. Not all of them, but some of them. So as soon as we plug any numbers into that expression, make it negative. Fn, 79 newtons downwards. We're going to make that negative because the normal force or the force of tension acts down. The force of gravity, well, it's m times g. It's 0.98 times 9.81. We're going to make that negative because it acts downward. So now we're going to solve for v. Okay, get this number on the right-hand side. That's easy enough. Multiply it by 0.4. Divide it by negative 0.98. Square root it. And when you do that, you should end up with v equal to 6.0 meters per second. Ask me that question later on if you're not able to get that 6 meters per second. Okay, I'll help you out with the rearranging a little bit more. Does that make sense to people? Okay, I want to try one more quick problem, and then we'll wrap it up there for the day here. It involves what we call minimum speed. If I've got these keys swinging in a vertical circle, like I always use as an example, okay, the keys are swinging in a vertical circle. Right now, these keys are going plenty fast in order to stay in the vertical circle. They've got enough inertia, got enough momentum, I should say, to keep going in a vertical circle here. But watch what happens when I slow the keys down a little bit. Okay, still staying in the circle, right? Slow them down now, all of a sudden, they don't go in a circle anymore. How come? Because they're not moving fast enough to stay in that circle, right? They're not moving fast enough. Below a certain speed, they won't stay in the circle. You would hate to be the guy on the roller coaster when the roller coaster cart wasn't going fast enough to go around the circle. The good news is there's a safety mechanism that even if that did happen, which it wouldn't, the cart would essentially be locked onto the track. So it could theoretically even stop upside down, and you'd be scared to death, but it would be safe for you. Okay? But if there isn't that safety mechanism, then yeah, if it's not going fast enough, it'll fall out of the loop. Okay, we don't want that to happen. Pay attention to the string again here for a second that are holding my keys. As I slow it down, right now the string has to pull the keys inwards. But as I slow it down and slow it down and slow it down to the point where the keys just barely make it in the circle, how hard is the string pulling? What's the tension in the string when the keys are barely going around the circle? How hard does the string have to pull, Lewis? Not at all. When you're going the minimum speed, the string doesn't have to pull at all. When the roller coaster is going the minimum speed around the track doesn't have to push at all. So at that point, to find the minimum speed that it has to be going in order to not fall into the circle, we're going to set Fn equal to 0. We're going to automatically make the normal force 0 because the string doesn't have to pull, the track doesn't have to push. That leaves us with one example here. A 700-kilogram roller coaster full of people goes around a vertical loop that has a diameter of 50 meters. Careful with that. The diameter is 50 meters. We want the radius, right? So the radius is 25.0 meters. What's the minimum speed at the top of the circle to stay on the track? So here's the roller coaster, top of the loop. Normal force acts down. Gravity acts down. We're going to say F net is equal to the sum of the forces, Fn plus Fg. But when we're looking for the minimum speed, Fn is 0. The track doesn't have to push at all. So it becomes mv squared over r equals m times g. Now, technically, both of those are negative values, right? Lewis asked the question, though, when we were working on this before, if they're all negative, do we have to make them negative? I do, just as a matter of habit. But if we made those both positive, we could get away with that. Masses cancel, by the way. That's good news. You go on that roller coaster tomorrow and you sit beside the really big, heavy guy that's 300 pounds. You don't have to worry that he's going to cause it to fall into the loop any more than the 130-pound guy is. The mass doesn't matter. The mass cancels. Doesn't matter how heavy the cart is. If it's going to go around the circle, it's going to go around. If it isn't, it isn't. V, by the way, we're solving for. R is 25. G is 9.81. Now, technically, both sides of this should become negative because they're both acting downwards, but the negatives cancel. Let's solve for V here. V squared is 9.81 times 25. And then V is the square root of 9.81 times 25. That's going to give me somewhere in the range of 15.66, or we'll round out to 15.7 meters per second. So you going above 15.7? Great, you're going to stay in the circle. You're going below that? Watch out, because you're going to fall out of the loop then. If you're a roller coaster designer, you can see how this might be useful to be able to do these calculations, right? All right. I won't leave you with any homework here for this, guys. Just finish up the other two questions that we assigned before. If you haven't finished them up already, we'll pick this up when we get back to class after our field trip tomorrow.